Lessons 1 and 2, patterns of growth. So the first thing you're going to do here is you're going to look at these patterns of a pattern growing, and you're going to fill out this chart. So here is stage. We have listed stage 2. We don't have stage 1. You have to, stage 1 would be just one single triangle. We could draw that in here. That is stage 1. So that's why we have stage 1 here, and y is the number of triangles. So first you're going to describe what do you see happening with the pattern? What is happening each time? And if you look closely, you will see that each time there are, here's the former stage 2, and 3 more triangles were added. And then we have what was stage 3, and again 3 more triangles added. So every time we go to a new stage, 3 more triangles were added. So we have 4 triangles here. 4 plus 3 is 7, 10, and 13. And so we see here that each time, again, we're just adding 3 to the previous input. I'm sorry, to the previous output to get the input. So we would call this, when you're adding the same number each time to get the next output, we call that a constant rate of change. So the rate of change is constant. Now let's look at this situation. Here we're going to see what is happening to the pattern in each stage. So number of triangles, and we're going to say number of purple triangles, not the white triangles that are created. So here we're going to start actually with stage 0. Stage 0, if we can imagine it, would have just been an entire filled-in triangle. And so there's just one triangle for stage 0. And then that triangle gets split into 3 triangles. So there'd be 3 triangles here. And then each of those triangles gets split into 3 more triangles. So now there's a total of 9 purple triangles. And then 27, and then 81. So if you're describing what's happening here, you're multiplying by 3. Each stage is 3 times more triangles. So here, if we go from one output to the next, instead of adding 3, we're multiplying 3 each time. So we call this, when you multiply by the same thing every time, we call that a growth factor. We're going to say that is a growth factor. And in this case, the growth factor equals 3. So now we're going to write the equation. So it might help to actually graph this first. So you're going to go down here and you're going to graph all the points. So we can write these points as ordered pairs, right? And maybe I will do it off to the side here. This ordered pair will be 1, 1, 2, 4, 3, 7. So the x-axis is the stage that we're at. The y-axis is the number of triangles. And we can graph our points, right? At stage 1, there's 1 triangle. At stage 2, there's 4 triangles. At stage 3, there's 7 triangles. And so we can see here, if we were to trace this backwards to try and find, this is a line, right? And if we were to trace that line backwards and use that same slope, we would see that the y-intercept was right here at -2. So we can write our equation in a number of different ways. We can think about it differently, but it might be helpful to look at the line. We know that if it's linear, it can be written in the slope-intercept form of an equation, y equals mx plus b. The slope, as we can see from the graph, is up 3 over 1. So it's going to be 3x. And then the y-intercept we just saw was -2. So 3x minus 2 is going to be our equation. And this is a function because for each input, there's only one output. Now, if we go over here and we graph this one, Notice here on this graph that the scale is different. Along the bottom, each square is equal to 0.25. Along the y-axis, each square is equal to 2. 2, 4, 6, 8. Because we're going to need a y-axis that goes up a lot more because the outputs really get big with this type of function. So let's go ahead and graph the points. At stage 0, we have 1 triangle. At stage 1, we have 3 triangles. At stage 2, we have 9. At stage 3, we have 27. Oh, wait, hold on, I'm graphing this wrong. I'm sorry. Didn't pay attention to my own. Sorry, at stage 0, we have 1 triangle. Here's stage 1. At stage 1, we have 3. At stage 2, we have 9. Stage 3, we have 26, 27, right? So we can start to see it's not a line, it's going to be a curve. This is going to be an exponential function. And its equation, notice here, each of these, we're going to take this growth factor. If we take the growth factor and we raise the stage to that factor, or we say, here, I'm going to tell you the equation is 3 to the x, and let's check this here. 3 to the 0, is 3 to the 0 equal to 1? Yes, it is. How about 3 to the first power? Does that equal 3? Yes. Does 3 to the second power, or 3 squared, equal 9? Yes. All right, so this is working. That is our equation. And this is also a function, because there's 1 output for each input. Now you're going to answer these questions. I'll do a couple of them with you. The input is always the x, and the output's always the y. And the input is also always the independent variable, the x. So in this case, the stage number. And the y, the output, is the dependent variable. We already answered this question. It is a function. How is the rate of change related to the graph? So our rate of change here, constant rate of change, is 3, positive 3. How is it related to the graph? Well, it is the slope of the graph. So let's write this up here. Rate of change is also the slope. And we learned that in our last unit about speed. Someone's speed, their distance divided by time, is their rate of change. And that is the slope of the line you would draw on a distance versus time graph. You'll answer these on your own. So now let's fill in this part here. We have, make this smaller. This example is a linear function. It makes a line, and it has a constant, as we said before, rate of change. In other words, a slope, a constant slope. And this is our general equation, which we've seen many times before. M is our slope, B is our y-intercept. And this is an exponential function. And exponential functions have a constant growth factor. They grow by the same factor each time. And this time it tripled each stage. Growth factor. And the general equation here is y equals a times b to the x. And notice the x here is in the exponent form. And I think I accidentally made this too big here. So this should be a and b should be here. Got pushed to the other page. A, in this case, is the initial value, meaning it is the starting, when x equals 0, it's what y equals. It's y equals when x equals 0. We can see it in our graph here. Here's when x equals 0, y equaled 1, right? And if we go up to our stage, it was stage 0. The initial value at stage 0, and this particular one is 1. It's one triangle. So it's the initial value. It also happens to be the y-intercept, right? Which makes sense because that is when x equals 0. X equals 0 always when a graph crosses the y-axis. And then our b, that's where we're going to see our growth factor. So for this equation here, here's our equation. I'm going to write it down here. Y equals 3 to the x. Let's see if it follows that general rule of y equals a times b to the x. All right, so a in this case is the initial value, which is 1, right? That's stage 0, when x is 0, when the input's 0, there's a one triangle. And then the growth factor is 3. It triples each time, raised to the x power. Is that the same as this? Yes, it is. We just have that sort of invisible times 1. So yes, we met that criteria of the general equation for exponential growth. Now here, you have two new equations for exponential growth. And they are in the form y equals a times b to the x. This one is in that form, and this one is in that form. So we're going to find a few ordered pairs here. We're going to plug in a few different inputs, values of x, and we're going to plug them into our equation. All right? So let's go ahead and do that. So if x is 0, what does f of x equal? And remember, f of x is another way to say y. When x is 0, f of x is 2 times 3 to the 0. Anything to the 0 power is 1. So it's 2 times 1, so it equals 2. So the ordered pair is 0, 2. Okay? When x is 1, we're going to plug it into our equation. 2 times 3 to the first power, which is 2 times 3, which equals 6. So our ordered pair is 0, 6. There we go. Last one, 2 times 3 to the second power, which is 2 times 9 equals 18. So our ordered pair would be 0, 18. Let's go ahead and we're going to graph this over here. So the first one is over 0, up 2. The next one, oh, wait, I made some mistakes here, sorry. This, the x value is 1, and here the x value is 2. Okay, so our next point is over 1, up 6. And the next one is over 2, up 18. So these go up by 1, so 16, 17, 18. There we go. So that is a curve. Right? Let's see, what is the starting amount when x is 0? So the initial starting amount or initial value is 2, right? When x is 0, y, or the output, is 2. The growth factor, how much is it growing by each time? Let's see, 2 times 3 is 6. 6 times 3 is 18, so the growth factor is 3. And if we plug it into our general equation, that works, right? Our growth factor, our starting amount is 2. And then, sorry, not our growth factor. Our initial value is 2, also the y-intercept. And our growth factor is 3. Now you're going to do this one on your own. You're going to do the same thing where you're plugging in the x, but now it's into this new equation, which is a little different. We've switched the a and the b here. We're going to see how that makes things different. You're going to determine the starting amount and the growth factor. And then you're going to answer this question. And then these you're going to do on your own. You're going to determine if each table shows a linear relationship, exponential, or something else. So what you're going to have to do here is figure out the difference. Is this multiplying? Is it a constant growth factor? Are you multiplying by something? Or is it a constant rate of change? You're adding or subtracting something. That's how you're going to determine. Let's do one together. 5, to get from 5 to 15 and 15 to 45, that's multiplying by 3. We have a lot of examples of multiplying by 3. It's not, the growth factor is not always 3. So it's a constant multiplying, constant growth factor. That would be, means it's exponential. And then the growth factor would be 3. So this could be, it could also be something that's neither linear nor exponential. And then the last thing, you're going to look at these 3 representations of an exponential function, a table representation, the equation, and a word explanation. The area of bacteria triples each day. And you're going to explain where you see the growth factor in each. Where do you see the growth factor in the table? Where do you see it in the equation? Where do you see it in the situation? So think about that, fill that out.